Well, you know a good deal of mathematics by now, and we're going to prove it to you in this program. What we're going to do is to tell you a very sophisticated mathematical story, one that usually gets told much later on in a course. And yet, you're going to be able to follow it with just the math that you've learnt up to Unit 4 of Block 2. Well, see if you can make the connections with Block 2 as we go along. Now, my story involves just these three shapes. And what I'm going to do is I'm going to weigh them. And they've been cut in order to fit under the graph of the function x maps to 1 over x. Well, my first piece is this shape. It fits under the graph of the function x maps to 1 over x between x equals 1 and x equals 6. And my second shape is this area. It goes from x equals 1 to 3. Well, of course, you wouldn't be in the least surprised if I tried to balance the large piece by adding the missing bit from 3 to 6. But, in fact, I'm not going to do that. My third piece is this, which fits here, from x equals 1 to 2. And when I add this piece to the left-hand pan, well, look, they balance anyway. Well, so what, you're probably saying. You can always get 3 pieces of card to balance. But all my pieces started from 1. And there is a rule about where they end. On the left-hand pan, I had a piece which ended at 2, plus the piece which ended at 3. And how far did I have to go along to find the piece which balanced? Well, we saw that I had to go along to 6. Now, 2 times 3 is equal to 6. Could that be the rule? Well, let's look at another case. So I'll throw this piece away, and I'll put the 1 to 3 piece on the right-hand pan. So now the situation is this. I have the piece from 1 to 3 on the right, and the piece from 1 to 2 on the left. Now, what do I need to balance those if my rule is going to work? Well, I'm going to need the piece from 1 to 1.5, because 2 times 1.5 is equal to 3. Well, here is this piece from 1 to 1.5, and when I put that in the left-hand pan, I get it to balance. And so, in fact, my rule works. The rule always works. In order to find what balances these two endpoints, I simply multiply them together. So there's a connection between the addition of areas and the multiplication of their endpoints. And this is where the mathematical story really gets exciting, because you've already met this rule in a different guise in Block 2 before. Well, perhaps if I use some different notation to describe it, you might recognize it. I've denoted the weight from 1 to r by W of r. And in terms of W, my first demonstration showed that W of 2 plus W of 3 was W of 6. And my second demonstration showed that W of 1.5 plus W of 2 was W of 3. In both cases, I was illustrating this general rule. W of r plus W of s equals W of r times s. You've seen this kind of rule before in Unit 1 of Block 2. Well, it's just the rule for the logarithm of a product, rs. And you've probably guessed that when I've been weighing shapes, what I've really been doing is measuring areas. So the area up to rs splits up into the area up to r plus the area up to s, just like the logarithm rule. In fact, the conclusion of our mathematical story will be that the area, A of r, is precisely the logarithm of r to a certain base. Well, part of our evidence for this will be this logarithm rule, which we're going to establish rigorously later on. But the other part of our evidence is numerical, and we'll tackle that first. What I'm going to find is the value of A of r for some positive r. Well, it's easy enough to find the area of squares and rectangles and so on, but how do I find the area under a curve? Well, the method we're going to use is to approximate that area using the areas of squares and rectangles and areas that we already know. And we'll take the case when r is equal to 2, so we're going to evaluate a of 2. Mike.
Here's our area, A of 2. We've called it A for short. I've divided it up into 4 equal strips and drawn these 4 rectangles to cut the top of the curve. And that gives me something which looks rather like a histogram. Now, it's very easy to calculate the area of a histogram because it's just the sum of rectangular areas. And that will give me an approximation to the area that I want. For example, look at this left-hand strip. The rectangle doesn't cover quite enough area as it should on the left here, but it compensates by covering a bit more than it should on the right. So that gives me a reasonable approximation to the area of that strip. So unfortunately, I can't tell how good an approximation it is. No matter where I position the top of the rectangle, I can't tell what these 2 odd little areas are. And I don't even know whether I've got an overestimate or an underestimate, except in extreme cases. And that's the clue. We consider 2 special extreme cases. One in which the top of the rectangle just comes above the graph, like that, and the other in which it just fits below the graph, like that. If we do the same thing for all the rectangles, we finish up with these 2 pictures. In this one, the tops of the rectangles fit just underneath the graph, and this will give us an underestimate because our area completely encloses the rectangular areas. And this one, the tops of the rectangles fit just above the graph, and this will give us an overestimate because the area is completely surrounded. So if we calculate the areas of the 2 histograms, we'll get 2 numbers, and the value of the area A will be pinched between those 2 numbers. Actually, with only 4 rectangles, it won't be pinched very tightly. But we'll see in a minute that by taking more and more rectangles here, we can get estimates which pinch A tighter and tighter. But first of all, let's find numerical values for our 2 estimates. And we'll start with the underestimate. The width of each rectangle is 1/4. And we can calculate their heights using the formula for the graph. And now we can calculate the areas of the 4 rectangles. So our underestimate is the sum of these, which works out to 3 decimal places as 0.634. So we know that the area we want is greater than 0.634. And we can calculate the overestimate in a similar way. This works out to 3 decimal places as 0.760. And this is greater than the area we want. So we've got our area trapped in this interval. This picture summarizes the situation. A lies between this underestimate and this overestimate. In other words, A lies inside this closed interval. And that's the situation for 4 rectangles. But earlier, I said that we can pinch A inside smaller and smaller intervals by taking more and more rectangles. The construction is exactly the same. We just divide this width into more and more strips, 8, 16, and so on. And in each strip, we draw the rectangle which just fits underneath the curve for the underestimate, and the one which just fits above the curve for the overestimate. Now, why does that give smaller and smaller intervals for A? To see why, we're going to go back to the logical beginning and take just 1 rectangle. Then we'll take 2, and then 4, like this, 8, 16, and so on. With only 1 strip, the underestimate is the area of this rectangle, which is 0.5. and this is less than the area A. And our overestimate is the area of this rectangle, which is 1. And this is greater than A. Now, if we divide the strip in two, our underestimate will be these two rectangles. And notice what's happened to our original underestimate. It has increased. It's gobbled up more of the area. So the new underestimate is a better estimate for the area than the old one. Its value is 0.583 to 3 decimal places. So A is greater than 0.583. For our new overestimate, we take two rectangles touching the top of the graph in each strip. So our original overestimate has decreased. We're not overestimating by so much now. In fact, its value to 3 decimal places is 0.834. So A is less than 0.834. And if we continue subdividing our strips, the underestimate will increase each time and the overestimate will decrease, like this. With 4 strips, our underestimate is this area, so our previous underestimate has increased by these two rectangles. The new value is 0.634, as we saw earlier. And our overestimate changes to this area, so it has decreased by these two rectangles. The new area is 0.760, as we saw earlier. And so on. Our underestimate will increase each time we subdivide. And our overestimate will decrease each time. So we get a sequence of intervals. On the left-hand endpoints, that's these numbers, are getting bigger. On the right-hand endpoints, are getting smaller. And so A is trapped inside smaller and smaller intervals. This is what we've called a nest of intervals in the past. You see, each interval lies inside the previous one. And in fact, we can make the ends of the intervals as close together as we please, and so calculate the value of A as accurately as we please, simply by taking enough rectangles. So if we go on from here with 16 rectangles to 32 and 64 and so on, when we get as far as 2048 rectangles, which is so many that they don't show up in the diagram, we finish up with this interval. And so we know that A lies between 0.693 and 0.694. Now that's the best we can do working to 3 decimal places. But we could calculate A as accurately as we pleased, simply by working to more decimal places and by calculating more intervals.
Well, you won't be surprised to learn that Mike's method works for the areas under more general functions than just x maps to 1 over x. Well, our story, let's get back to that. What we're looking for is evidence that the area from 1 to r is the logarithm of r. And so what I have to verify is that A is log of 2. Well, I can tell you straight away that it's not log of 2 to the base 10, because that number is about 0.30. And what we're looking for is a number that lies between 0.693 and 0.694. But if you look into any standard book of tables, you'll find that there's another table of logarithms, logarithms to the base e. Now, e is that number that we asked you to calculate earlier on in the block. Its value is about 2.72. Logarithms to the base e are called Neperian logarithms. And the value of logarithm of 2 to the base e does agree with our estimate of the area. So that's the numerical part of our evidence that A of r is precisely log of r to the base e. Now, don't forget the other piece of evidence is the logarithm rule for the addition of areas. Well, we haven't proved that yet. Remember, I just showed that it worked by weighing in a couple of cases. So Let's go ahead and prove that rule now.
Remember, what I have to show is the area up as far as R plus the area up as far as S is the area up as far as R times S. Now, there's no way in which I can fit the two small areas together to make the large area. Instead, what I'm going to do is to show you how you can distort this shape so that it just fits into this region without changing its area. And to do that, I'm going to use the ideas of scaling in the x and y direction. Remember, that means stretching the distances of points from the x and y axes. Now, that's what happens to distances when we scale. But if I scale a region, what will happen to its area? To find out, let's look at rectangular areas first. The simplest case is when the rectangle is butted up against the origin. Let's scale this in the x direction by a factor of 2 and see how its area changes. All distances from the y-axis have been doubled, so the width has been doubled. And the height is unchanged, so the area has doubled. And this would hold for any rectangle. It doesn't necessarily have to touch the origin like this one. To see why, let's look again at the scaling by 2, but let's concentrate this time on a part of the original rectangle. The area has still doubled, because the width has still been multiplied by 2. Area gets multiplied by the factor we scale by. And the same holds for scaling in the y direction. For example, let's scale this rectangle by a factor of 1/2 in the y direction. The area gets halved, because the height gets halved. Again, area gets multiplied by the factor we scale by. Now, that rule works for any areas. If I scale a region in the x or the y direction by a certain factor, then its area gets multiplied by that factor. Now, that shouldn't be too surprising. If it works for rectangles, then in view of what we've seen earlier, it should work for any area, because any area can be approximated by rectangles. What I'm going to do is to take this region up as far as R, scale it by a factor S in the x direction, and that will multiply its area by S. And then I'm going to scale the result by a factor 1/s in the y direction. And that will multiply the area by a further factor 1/s, and I'll get back where I started. I'll end up with a different shape, but it'll have the same area. And in fact, the shape that I finish up with will just fit here in this blank space from S to RS. Now, to see why that works, we're going to have to look at the curve and see what happens to that when we carry out the two scalings. When we scale in the x direction by a factor S, the distance from the y-axis of each point gets multiplied by S. Now, what's this new graph? Well, remember that in general, if we start with a function f, then when we scale by a factor s in the x direction, f of x changes to f of x divided by s. So when f of x is 1/x, as it is here, it becomes 1/x divided by s, which is s/x. So the new graph is x maps to s/x. Now let's scale by 1/s in the y direction. And you should remember the effect of this. The new values will get multiplied by 1/s. So the final graph will be x maps to 1/x again. Now, let's see that again. But this time, concentrate on the area from 1 to R. When we scale by s in the x direction, the area gets multiplied by s. And when we scale by 1/s in the y direction, the new area will get multiplied by 1/s. So we end up with a of r again. And that's proved our logarithmic addition rule, because we can now represent the area A of R in this new position, and add this area to it, which is A of S, to get the total area from 1 to RS, the area A of RS.
And so this logarithm rule for addition works in general. And that's the final piece of evidence that we're submitting in our contention that the area under the curve x maps to 1 over x from 1 to r is in fact the logarithm of r. In fact, the logarithm of r to the base e, because we showed that the area from 1 to 2, a of 2, was log of 2 to the base e. Now, I find that incredible. We started off by talking about areas, and here we are finishing up talking about logarithms. And it's especially surprising if you remember how we defined logarithms way back in Unit 1. Remember, whatever your base is, in our case it's base e, we defined logarithm to the base e as being the inverse function of the function x maps to e to the x. In fact, the rule that logarithms change multiplication into addition is derived from this law of indices. So there must be a connection between the function x maps to e to the x and my function x maps to 1 over x. Well, of course, there is a connection, and that will be explored in Block 3 in the calculus, where we take up the whole story again. But we don't want to give you a preview of Block 3 now. We're really more interested in taking out some ideas from Block 2. And from what you can see, the two main ideas in this program for Block 2 were the ideas of scaling and nests of intervals. So let me conclude the story by telling you where these two ideas came in. First of all, scaling. We used the idea of scaling to establish this logarithm rule. We showed that the area from 1 to r could be distorted to the shape from S to RS by using scaling twice, and of course we don't change the area. So that's how scaling came in. Now, how did nests of intervals come in? Well, we showed that the logarithm involved was log of r to the base e, because we evaluated the area from 1 to 2 as log of 2 to the base e. Now, how did we do that? Well, remember, what we did was we approximated to the area A by using sums of rectangles to get overestimates and underestimates, and so we got a nest of intervals. Now, this idea of using a nest of intervals to get the number that you're interested in is very important, and it's come up again and again. We saw it in Block 1 when we used the bisection rule to define root 2, to calculate root 2, and in fact we saw it in Block 2 where we used it to get 2 to the root 2, I think it was. And here we've got it again when we're actually using it to specify the value of an area. So it's very important. In fact, from what you've seen, you wouldn't be surprised if I told you that this idea of using nests of intervals to specify a real number is one of the most important ideas in our understanding of the real number system.